I can't stand the rain against my window.
The goal of this lecture is to say something about the proof of the classification of modules over a PID. But in order to do this proof, we're going to need some preliminary results. And the first thing that we're going to do is prove a generalization of something that we proved when we were talking about the proof that every PID is a UFD. So let's define a Noetherian R-module. A left R-module M is a Noetherian R-module, or we say that it satisfies the ascending chain condition on submodules if there is no infinite increasing chain of submodules. What that means is that if M1 is contained in M2, is a submodule of M3, and so on, is an increasing chain of submodules of M, then there's a positive integer M past which it stabilizes, little m, such that for all k greater than or equal to little m, mk equals mm. So what does that mean? You hit this positive integer mm, and you stabilize past that point. Mm equals m plus 1 equals m plus 2, and so on. So now we can say what it means for a ring to be Noetherian. A ring is Noetherian if it is Noetherian as a left module over itself. So what does that mean? No infinite increasing chain of submodules. Submodules of this module R as a ring left R module over itself are left ideals of R. So that means that there's no infinite increasing chain of left ideals of R. And this now matches up with the definition of Noetherian that we gave when we were discussing this proof that every PID is a UFD back in Chapter 8 near the beginning of Math 206b. All right, so what we're going to prove is Theorem 1 in section 12.1. Let R be a ring and M a left R module. Then the following three things are equivalent. 1, M is a Noetherian R module. 2, every non-empty set of submodules of M contains a maximal element under inclusion. And 3, every submodule of M is finitely generated. So how does this match up with what we did before? Before, we proved 3 if and only if 1 for the case where you take M to be a left R module over itself. So that a ring is Noetherian if and only if every ideal of R is finitely generated. Okay, so we'll prove this by proving 1 implies 2 implies 3 implies 1. And what's the reason, before we focus just on 1 and 3 for rings, what's the reason to include 2 here? This is the statement that we're actually going to apply in the proof of the existence part of the classification of modules over a PID. So I'll pause and erase, and we'll talk about this proof. Let's first do the proof that 1 implies 2, that M is a Noetherian R module implies that every non-empty set of submodules of M contains a maximal element under inclusion. All right, so let's assume M is Noetherian and let sigma be a non-empty collection of submodules of M. We're just going to pick some elements in sigma, M1. And if M1 is maximal under inclusion, then we're done. And if not, what does it mean to not be maximal under inclusion? Then there's some M2 in sigma with M1 properly contained in M2. Okay, well, if M2 is maximal under inclusion, we're done. And if not, that means that there's some M3 in sigma with M1 properly contained in M2, properly contained in M3. We can keep doing this. Continuing in this way, if 2 is false, if we don't have a maximal element under inclusion, then every time we add a new submodule to the chain, we can add another one, and another one, and another one. So if 2 is false, then what can we find? We can find an infinite sequence of increasing submodules in this collection sigma. M1 contained in M2, contained in M3, and so on. And this contradicts the assumption that M is Noetherian, that M satisfies the ascending chain condition on submodules, because sigma consists of submodules of M. So we found an infinite increasing chain of submodules in M. So this completes the proof that 1 implies 2. So I'll pause and erase, and we'll do the other two pieces, that 2 implies 3 and that 3 implies 1. Let's do the proof that 2 implies 3. So let's assume that 2 holds, that every non-empty set of submodules of M contains a maximal element under inclusion. And let's use this to prove that every submodule of M is finitely generated. So let's pick a submodule N of M, and our goal is to show that N is finitely generated. So the clever idea of this argument is to let sigma be the collection of all finitely generated submodules of N. Okay, first, we know something about non-empty collections of submodules. So let's see that this is non-empty. 0 is in N because N is a submodule. So certainly there's at least one element in sigma. All right, so now what happens when we apply 2? We see that sigma contains a maximal element n prime. And we're going to use this n prime, which we know is finitely generated, to show that n is finitely generated. How do you do that? Well, if n prime equals n, then we're done. Then n prime is finitely generated, so n is finitely generated. So if not, then that means there's some element x in n that's not in n prime. So let's take the submodule of n generated by this maximal element n prime together with this single element x. And the submodule generated by n prime and by x is finitely generated. Take a finite generating set for n prime, add the element x, and now you have a generating set for this submodule that is size finite plus 1. It's still finite. So what's true about this submodule? Well, it certainly contains n prime, and it also contains x, and it's finitely generated. So it should be in this collection sigma, because it's finitely generated and it's a submodule of n. So we get this submodule that properly contains n prime and is in sigma. So that means that n prime was not actually a maximal element of sigma under inclusion, because we found something in sigma that includes it. So this is a contradiction. What are we contradicting? We said if n prime is equal to n, we're done. And if not, something happened. And that's what we're contradicting, that there was some element x in n minus n prime. So we conclude that n prime equals n, and that n is finitely generated. Okay, so in order to remember this argument, the main thing is to remember what collection sigma to take. So I'll pause and erase, and we'll do the final part of this proof, that 3 implies 1. Let's finish the proof of this theorem by proving that 3 implies 1. So let's assume that 3 is true, that every submodule of M is finitely generated. And what we want to prove is that every infinite increasing chain of submodules of M must stabilize. So let's take a chain of submodules of M, M1 contained in M2, contained in M3, and so on. And the big idea here is to consider the union of this infinite chain of submodules. We'll call that N. And you can check using, for example, the submodule criterion that N is a submodule of M. I won't do the details here because we've done a very, very similar argument for a union of a bunch of ideals in a chain. So you really should check this for yourself. Now, applying 3, what do we know about N? It's a submodule of M, so it's finitely generated. So let's write down a finite generating set for it. It's generated by A1 up through AN, a bunch of elements in M. And since AI is in M, N is the union of this infinite set of submodules, AI has to be in one of these submodules. So AI is in MJI for some positive integer ji. So we get J1, J2 up to Jn, telling us where we're picking up each of these generators in this chain of submodules. And we're going to define little m to be the maximum of this set of integers. All right, so now let's look inside of the particular element of the chain, m sub little m. And because each element of this chain is contained in all the ones that come after it, if ai is in mji, then it's in mk for all k greater than or equal to ji as well. So this maximum contains all of a1 up through an. So if it contains all of these elements and it's a submodule, it contains the submodule generated by all of these elements. But the submodule generated by all of these elements is n. So n is contained in this m sub little m. And because n is a union of this infinite chain, in particular, it contains everything that's in m sub m. So clearly m sub m is in n, so they are equal. And then if you already have n, and then you have a bunch of things that are submodules of n containing n, then everything past that point is also equal to n. So n equals m plus 1, m plus 2. This chain has stabilized when you pick up all of n at this integer m. And that says that m is a Noetherian R-module that every chain stabilizes. It satisfies the ascending chain condition on submodules. All right, so I just want to point out one thing to emphasize, which is we've seen examples. In general, submodules of a finitely generated R module M need not be finitely generated. What was the example we saw? If you take the polynomial ring in Q adjoin countably many variables, that's a ring R, and you can think of it as a left module over itself. And the submodules then are ideals. And that ring contains an ideal that's not finitely generated. The whole ring itself is finitely generated as an R module over itself. It's generated by 1. So certainly it's finitely generated, but it contains a submodule that is not finitely generated. But when you have an R module M that is Noetherian, all of its submodules are finitely generated. So one thing that's telling us is that that example is an example of a module that is not Noetherian. So in the case that your R module is Noetherian, all of its submodules are finitely generated. So this is saying whenever you can find one of those examples where you have a submodule that's not finitely generated, where you have, say, an ideal of a ring that's not finitely generated, you're looking at something that is not Noetherian.